The problem statement from GATE Physics 2014 reads as follows. If the half-life of an elementary particle moving with speed 0.9 c in the lab frame is 5 into 10 to the power minus 8 seconds, then the proper half-life is dash 10 to the power minus 8 seconds. Speed of light c is given to us as 3 into 10 to the 8 meters per second. This is a numerical answer type question. We'll try to find our answer, fill in the blank over here. Let's have a quick look at the concept of time dilation. So let's say the problem statement is so these are the two mirrors, okay, the top mirror and the bottom mirror. So we want to identify, we want to measure the time which is taken by a photon to reach from the top mirror to the bottom mirror. That means we need, let's say this length is L, right? This length is L. So there is an observer sitting in the cart. So they are trying to measure the time taken by a photon to travel from this top mirror to the bottom mirror, and this whole assembly is moving in the right with a constant speed v. So this is an inertial frame, and this v is it cannot be ignored in when compared to the speed of light. So it's comparable to c, and we are interested in finding this time, that what is this t prime, right? Now such a time when measured is called the proper time. Why? Because we are sitting in the object's frame. So the object here is the mirror, right? So we are sitting in the mirror is attached to the cart, and we are sitting in the cart itself. So we are traveling with the object, and when we are traveling with the object, when we are at rest with respect to the object, what we measured is a proper time. So whatever time is being measured by this fellow over here, they'll measure the proper time for the proper time taken by the photon to reach the bottom mirror from the top mirror. And the same assembly now will be observed by another observer. Let's call this observer 2. So this observer 2 observes that this is the top mirror and this is the bottom mirror. So this observer sees, so this observer will also measure time, the same time taken by photon to reach from the top mirror to the bottom mirror. Now note a key difference. What this observer will see is that this bottom mirror has moved to the right by some distance vt prime, because t prime is the time taken from the photon to hit from top to bottom. So this has moved a bit to the right, and we know the speed of time remains constant. So this observer measured that it takes delta t time, this time, to travel this, and this is the length L that we had measured. So you can clearly see it's just by simple Pythagoras theorem that delta t will be somewhat larger than t prime, right? So this is because when observing from the observer's frame, from the rest frame, is larger than the time measured by the observer in the frame of the object. Here we measure the proper time, here we measure the observed time, and observed time will always be greater than proper time, and dilation is a synonym for expansion. So time measured by this observer has increased as compared to time with this observer. Now this is just a conceptual understanding. Now what we'll try to put it in concrete mathematical terms. So we want to measure the time, right? The t2 minus t1, where t2 was the, let's say t2 was the timestamp when the photon hit the bottom, right? So let's call this event q. The coordinates may be x2 and t2, and this is p when the photon left the top plate. So the coordinates are x1 and t1, and this is the frame, is the rest frame, right, or the ground frame. This is the observed time. So the observer is sitting at O here, and we want to find what is this time, what is the value of this time. And we do know that this PQ system, right, is moving in positive x direction, is at some constant speed v. This is also an inertial frame. This is a constant speed. Then let's call this frame S prime, or we call this frame object's frame. This is called the object's frame. I reiterate that this whole assembly, this whole system is moving towards the right as a constant speed v. Okay. Now naturally this system will appear at rest here, because we have already given this velocity here, object's frame, right? So there again the same two events will be observed, p prime. Let's give this coordinate x1 prime and correspondingly t1 prime, and account q prime. Let's call this q2 prime and t2 prime. So these are the coordinates. This is the p prime is the coordinate when the photon left the top mirror, as observed by this observer O prime in the object's frame, in the cart's frame that we saw in the last slide. right? So the proper time definition is measured in object's frame of reference. So we are S prime is the object's frame of reference for co-local events. What do we mean by co-local? So P prime and Q prime, their space coordinates, that means X, Y and Z, have to be equal. So here we are ignoring Y and Z because we have assumed it to be one dimensional system in space. So what we'll see is that co-local events means x2 prime is x1 prime. That is the definition of proper time, right? So we find t1 prime is nothing but the time taken by the photon in S prime frame to move from top mirror to the bottom mirror. And delta x prime is x2 prime minus x1 prime, which is equal to 0, because this is the definition of proper time. Now, how do we find t when we know t prime and delta x prime? It's very simple. We need to find non-primed entities when we know the primed entities. This we can do by using the inverse Lorentz transformation. So we can find t2 in terms of t1 and x1, and similarly t2 can be found in terms of t2 prime and x2 prime. Similarly, t1 can be found in terms of t1 prime and x1 prime. So let's do that. The value of t2 will be gamma t2 prime. I'm using this formula, okay? So gamma t2 prime plus v x2 prime over c square minus gamma t1 prime plus v x1 prime over c square. So we'll get gamma t2 prime minus t1 prime plus gamma v by c square x2 prime minus x1 prime. Now x2 prime minus x1 prime is 0 by definition of the proper time here. So this term vanishes. So what we'll get is t equal to gamma t2 prime minus t1 prime. T2 prime minus t1 prime is nothing but t prime. So this implies we get t equal to gamma t prime, where gamma is the entity which is defined by this formula over here. So you can see gamma will always be greater than 1. So t, the time measured by this observer in frame S, will always be larger than the proper time, which is measured in the frame of reference of the object itself. So this is the takeaway from time dilation. Time has increased. This means the increase or expansion is a synonym for dilation, right? So this was the problem given to us. And before we solve any problem related to special theory of relativity, it's good to have some pre-checks. So what are those pre-checks? First is whether the frames mentioned in the problem are inertial or not. So first frame mentioned is inertial, the lab frame. So lab frame, this is the S frame or the lab frame. This is usually assumed to be at rest. So S is at rest. This means it is inertial, right? So what about the second frame? The second frame which we need to go into object's frame, right? Because there's a particle moving at speed 0.9 c. So this is the 0.9 c, and this is the what we call the particle frame. The particle frame, and denoted by S prime, right? So this S prime frame is also moving at a constant velocity. So this is also inertial, right? So S prime is constant v. This implies also inertial. So both the frames are inertial. That's good. This means we can apply all the Lorentz formula and which we talked about. So as far as moving frame is concerned, what is the speed and direction? The speed we know is 0.9 c, which is given in the problem because that's the particle is moving with that velocity, and the direction is, so we assume that this is the positive x direction, and so it's moving in positive x direction, or you can say I cap. Right? How many dimensions? So the question is silent about it. So we can simply assume it's a 1D system, because there's only we can assume that we can work with only the x direction. There's no need to invoke the y and z direction. So we assume it's a one-dimensional system with only x, and obviously a time remains the other coordinate. So here I'm talking about the space dimension. So only one dimension, which is x, right? So so as you can see now, here is the S frame, the lab frame in blue. So here a particle P is moving at 0.9 c. The particle P is denoted in color green. And when you go into particles frame, which is the red frame here, the S prime frame, this frame is moving at a speed 0.9 c with respect to the frame S, and naturally the particle P, which we now denote as P prime, everything is primed in the S prime frame. Here it will appear that ux prime, the speed is 0, which makes sense because we are in particles frame. So it will appear at rest in this to the observer O prime, because we are already in particle frame in the S prime frame. Right, and we are given half-life in lab frame. So in the blue frame we are given the half-life as 5 × 10⁻⁸ seconds, and we are required to find the proper half-life, that is half-life in particles frame. This is what we defined, half-life in particles frame. This is the proper half-life, and which we denote by t prime. We need to find out this entity. How do we find out this entity? We simply apply the formula, time dilation formula, t equal to gamma t prime. So t is given as 5 into 10 to the power minus 8. Gamma we need to find out, and t prime, so we'll get t prime equal to 5 into 10 to the power minus 8 over gamma. Now let's try to find the value of gamma over here. So gamma is 1 over 1 minus v square over c square, right? So this will be 1 minus 0.9 square c square over c square. So this gets cancelled. So this will be 1 minus 0.81. So this will be 5 into 10 to the power minus 8 over, the gamma's value is 1 over 0.19. So this will turn out to be square root 0.19 into 5 into 10 to the power minus 8. Okay, so let me calculate the value of 0.19, square root 0.19, sorry. So square root 0.19 is approximately 0.436. So this is 0.436 times 5 into 10 to the power minus 8. So this comes out to be 2.180 into 10 to the power minus 8 seconds. Okay, so this is, we found this is the t prime that we required. So I'll write it here. T prime was 2.180 into 10 to the power minus 8 seconds. We were required to find the units of 10 to the power minus 8. So we drop this term. So the only term here would be 2.18. So that depends on how many decimal places you want to put. So if it's 2 decimal places, it will be 2.18. If it's 1 decimal place, it will be 2.2. The question is silent. I'm just sticking to the two decimal places. So that is our answer. You notice that the proper half-life is much lower than the lab frame half-life, which makes sense because time dilation plays a role, because the particle is moving at a speed fairly close to the speed of light. So that's a complete problem. Thank you for listening.